You walk into a building, maybe it's your office, could be a school, a library, maybe a store. Take a second. How's the air feel?
Mm.
Is it fresh, stuffy, maybe
hmm
just a little off?
Yeah, we breathe it all the time without really thinking about it.
Right. But that indoor air quality, it has a huge impact on our health, our comfort, even like how well we can focus.
Absolutely. And making sure that air is, healthy and comfortable. It's not just left to chance. There are actually specific, pretty detailed standards designed to make that happen.
Okay.
And today, we're going to pull back the curtain on really one of the foundational documents for indoor air quality and ventilation design. It's called ASHRAE Standard 62.1.
Ah.
We'll be digging into the 2007 version based on the sources we have.
Okay, let's unpack this then. First off, what is HRA?
Right. So ASHRAE stands for the American Society of Heating, Refrigerating, and Air Conditioning Engineers. They're, a global professional group, and they develop technical standards, guidelines, that sort of thing.
Standard 62.1. It's what they call a voluntary consensus standard,
Meaning?
meaning it's put together through this big collaborative process. You've got engineers, architects, public health folks, building owners, all kinds of people involved. The goal is to get broad agreement.
Voluntary, you said, but you also hear it's widely adopted.
Exactly.
Oh.
Yeah, while it's not technically a law itself, 62.1 gets referenced or even directly written into building codes all over the U.S. and internationally, too.
Ah.
So designing to this standard, it's often not just a suggestion. It's usually a requirement to actually get a building permit and get it built.
Got it, got it. So what's the core mission here? What's this document trying to, solve?
The main purpose is to spell out minimum ventilation rates and other steps needed for what they call acceptable indoor air quality.
Acceptable. Okay, what does that mean in their terms?
Well, it's got a specific definition right in Section 3. It means air where there are no known contaminants at harmful concentrations.
Okay, health.
Right. And where a substantial majority, 80% or more, of the people exposed do not express dissatisfaction.
Huh. So it's not just about pollutants making people sick. It's also about things like smells, stuff that might just make people uncomfortable or complain.
Exactly. Health and comfort, that's really the dual goal.
Right. And who's this aimed at primarily? New buildings? Old ones?
It's mainly intended for regulatory use. So new buildings, additions, big changes to existing buildings. But it's also meant as a guide if you want to improve IAQ in buildings that are already standing.
Okay. It says it applies to most spaces intended for human occupancy. Are there any interesting places it doesn't cover?
Yes. And this is where it gets, really relevant for a lot of us day to day. There's an addendum 62.1F that lists specific exclusions.
Like what?
Single-family houses, for one. Also multifamily buildings, if they're 3 stories or less above ground. And vehicles, aircraft, those are out too.
Okay, so this standard sets the rules for the air you breathe in, say, your office tower, your kid's school, the hospital, the mall, maybe a tall apartment building.
Yeah.
But generally not your own house or a small apartment complex.
That's the key takeaway. It's mostly governing the air where lots of people gather or spend a lot of time, but typically leaves our homes out of its direct scope.
Fascinating. Okay, so our mission for this deep dive is clear. Let's unpack the key requirements, the concepts in this standard, so you, the listener, can get a handle on what goes into designing, building, and, importantly, maintaining good indoor air quality in those public and commercial spaces.
Yeah, let's dig into the why behind some of these rules.
Right.
And maybe a good place to start is a foundational idea. Before you even think about bringing air into a building, you have to look at the air outside. That's Section 4, outdoor air quality.
That makes sense. Garbage in, garbage out, right. Your source air matters.
Totally. The standard says, before you finalize the ventilation design, you must investigate the quality of the outdoor air right there at the site, and you have to document it.
Investigate how?
2 main ways. First, check if the region complies with national air quality standards. Like in the U.S., the EPA's NWAQS for pollutants like particulate matter, PM10, PM2.5, ozone, stuff like that. Table 4.1 lists them.
So basically, are you building somewhere that already has known air quality issues?
Right. But that's not all. You also have to do a local observational survey right around the building site.
Like boots on the ground?
Yeah, exactly. Appendix H even gives a template. You look for nearby potential contamination sources, exhaust vents from kitchens or labs, maybe garbage dumpsters, loading docks, cooling towers. You even look for visible plumes, note any weird smells, check the prevailing winds.
So you're literally scouting the neighborhood to see what nasty stuff might get sucked into your fresh air intake.
Pretty much. And the results from both the regional check and that local survey, they have to be documented, reviewed. If the outdoor air looks particularly bad,
Yeah.
it might mean you need extra filtration or treatment steps inside the building system.
Okay. So we know what we're starting with outside. Now, how does that air actually get in and move around? That brings us to Section 5, Systems and Equipment.
Right. So the standard actually allows for both natural ventilation,
Hmm.
opening windows, specific vents and mechanical systems using fans and ducts.
Can you just rely on windows?
Well, if you use natural ventilation, there are rules. Like
Mhm.
you need permanent openings, windows, vents, whatever, within 25 feet of the space they serve. And the total openable area has to be at least 4% of the floor area.
Ah.
There can be exceptions if you have like an engineered natural ventilation system, but
Yeah. So you can't say crack a window and call it done. There are actual design criteria even for that.
correct. And for mechanical systems, Section 5 lays out some really crucial design points. One key thing, the system has to be designed so it can be balanced,
Valid.
meaning you can adjust it to make sure it actually delivers the minimum required ventilation air even when things change, like occupancy. And another critical point, sometimes overlooked until there's a problem, Section 5.14 mandates access
Access to what?
to everything.
Hmm.
Air handlers, ducts, filters, cooling coils, drain pans, fans, sensors. All those components need to be reachable for inspection, cleaning, and maintenance.
Ah, that makes sense.
Because if you can't get to it, you can't maintain it. And poor maintenance pretty much guarantees poor air quality down the line.
That seems so simple, but yeah, incredibly practical. What about the stuff the air actually flows through, the materials used in the system?
Good point. Section 5.5 covers that. Airstream surfaces inside the equipment, the ducts they need to resist mold growth. They even mention standard tests for this, like UL 181.
Okay.
And they also need to resist erosion. You don't want bits of insulation or duct liner breaking off and blowing into the space.
Right, you don't want the system itself adding particles.
Exactly. The insight here is the system shouldn't become a source of contaminants, especially mold. And, importantly, it notes that even mold-resistant surfaces can grow mold if they're continuously wet.
That connects back to managing moisture, doesn't it? Which I guess we'll get to.
We will.
But first, maybe the part people see most from the outside, the outdoor air intakes. Section 5.6.
Yes. Location, location, location.
Yep.
This is absolutely critical. The idea is simple. Put the intakes where they won't suck in those local contaminants we just talked about.
Makes sense.
Table 5.1 gives actual minimum separation distances from potential pollution sources.
Okay, give me some examples, like how far away from everyday stuff?
All right, think about this. You need to be at least 15 feet away from, say, a garbage area or a loading dock.
15 feet. Okay.
At least 25 feet away from cooling tower exhaust. You know, that misty stuff. It's full of moisture, potentially bacteria like Legionella.
Right, definitely want to avoid that.
And significantly contaminated exhaust, like from a kitchen hood vent, needs 15 feet minimum. If it's really noxious or dangerous exhaust, that jumps to 30 feet.
30 feet, wow. And how do they measure that distance? Just straight line?
No, and this is interesting. It's measured as the shortest stretched string path.
Stretch string.
Yeah, imagine pulling a string taut from the source point to the intake point, going around corners or obstacles. It's a more realistic measure of how air and pollutants might actually travel.
Huh. That visual really helps. So you can't just stick the fresh air intake right above the dumpster or next to the lab exhaust. Seems obvious, but clearly needs to be a hard rule.
Absolutely needs to be. Then there's filtration, another key piece, Section 5.9.
Okay.
The standard requires particulate filters upstream of any wetted surfaces, like cooling coils. And the minimum efficiency is specified using the MRV rating. It has to be MRV 6 or higher.
MRV. What's that stand for?
Minimum efficiency reporting value. It's just a standard way to rate how well an air filter catches particles of different sizes. MRV 6 is relatively basic filtration, good for catching larger dust, lint, that kind of thing.
Okay, so minimum MR6 and before the cooling coil. Why specifically before the coil?
Because that coil gets wet from condensation when it's cooling the air. And if dust and dirt build up on a wet surface, that's a perfect recipe for mold and bacteria growth. So the filter protects the coil, which in turn protects the air from getting contaminated inside the system.
Ah, okay. Keep the wet parts clean.
Exactly. And it also says if your initial investigation found that the outdoor air itself is pretty bad, like high PM10 particulate levels, then you're specifically required to use MRV6 or higher filters on that outdoor air intake too.
Makes perfect sense. And speaking of wet parts, Section 5.10 gets into humidity control.
Right. This is important, especially in humid climates or certain building types. The standard requires that mechanical systems that dehumidify must be designed to keep the relative humidity in the occupied space at or below 65%.
65%? Why that number?
That's generally considered a threshold to significantly limit mold growth on surfaces and within the HVAC system itself. It reinforces that point about avoiding continuously wet surfaces anywhere in the system.
So it's not just about cooling the air. You might need active dehumidification just to stop mold.
Exactly. Under certain design conditions, like high outdoor humidity combined with low indoor heat load. And the building structure itself, the envelope, plays a part too. That's Section 5.15.
How so?
Well, the building skin needs barriers to stop rainwater leaks, obviously,
Huh?
but also vapor barriers to prevent moisture moving through walls and condensing inside them. And it needs to be sealed reasonably well against air leakage,
Why air leakage?
because uncontrolled leaks mean untreated outdoor air, plus moisture and pollutants, can sneak directly into the space, bypassing your filters and your controlled ventilation system entirely.
Gotcha. So the building structure itself is part of the whole IAQ system, not just the box the HVAC lives in.
Absolutely integrated.
Mm.
Now, once the air is inside, the standard recognizes something important. Not all air within a building is, the same quality.
Yeah.
Section 5.17 introduces air classification.
Air has classes, like first class, business class.
Sort of, yeah. But based on contaminants and odor. Class 1 air is considered pretty clean, low contaminants, inoffensive odor. Think of a typical office space. Class 2 air has moderate contaminants, maybe mild irritation or mildly offensive odors. Or it's just air that's not suitable to mix back into Class 1 spaces if they serve different purposes, maybe a beauty salon, certain lab areas, some retail spots.
Right.
Class 3 air has significant contaminants or offensive odors. Think air exhausted from commercial kitchen hoods or maybe a trash room.
Okay, so you're basically grading the air based on how dirty or smelly it is, and these classes determine where that air can go next.
Precisely. Section 5.17.3 lays out recirculation limits. The key insight here is just preventing cross-contamination.
Makes sense.
Class 1 air, you can recirculate it or transfer it pretty much anywhere. Class 2 air, you can recirculate it within its own space or transfer it to other Class 2 or Class 3 spaces, maybe restrooms. But, and this is crucial, Class 2 air cannot be recirculated or transferred back into Class 1 spaces.
So no nail salon air going back into the general office area.
Exactly. You want to keep that separate. And Class 3 air usually needs its own dedicated exhaust system and generally can't be recirculated into occupied areas at all.
Makes intuitive sense. Keep the potentially yucky air away from the clean air zones. What about something really specific like cigarette smoke?
Yes. Section 5.18. This was added via Addendum 62.1G, and it specifically covers buildings that have both environmental tobacco smoke, ETS areas, and ETS-free areas. It only applies if a building decides to allow smoking in designated spots.
So if you have a smoking room in an otherwise non-smoking building.
Exactly. And the standard is very clear here. It doesn't even pretend you can achieve acceptable air quality in the smoking area itself. The science says that's basically impossible with ETS.
So what does it require?
It focuses entirely on containment and separation. You have to clearly designate the ETS areas. You must make sure the non-smoking areas are at a positive pressure compared to the smoking areas, meaning air always flows out of the clean zones towards the smoking zone, never the other way around.
Like an airlock almost.
Kind of. You need physical air barriers. You absolutely cannot recirculate or transfer air from the ETS area to any ETS-free area. The exhaust from the smoking area needs to be handled properly. And you need signs warning people before they enter the ETS area.
So the principle is total isolation. Protect the non-smoking spaces at all costs.
That's the strategy. Isolate and contain.
Okay. So we've covered acceptable air, checking the outdoors, designing the system components, managing different air types. Now for the big question, how do you actually calculate how much ventilation air a space needs? Section 6 gives two main ways to do this, right?
It does. You've got the ventilation rate procedure, usually called the VRP, and the IAQ procedure.
Let's tackle the VRP first. Sounds like the main one.
It's definitely the more common prescriptive method. Section 6.2, think of it like a recipe book for different kinds of spaces.
A recipe book.
Yeah, it gives you minimum ventilation rates based on the space type, office, classroom, restaurant, whatever the number of people expected in there, and the size, the floor area.
Okay, how does that recipe work? Is there a formula?
Yeah, there's a core equation, equation 6.1, for figuring out the outdoor air needed right down in the breathing zone where people actually are. That's called VBZ. And the formula is VBZ equals RPPZ plus RAC as.
Whoa, okay, break that down.
It's simpler than it looks. The insight is that ventilation needs come from two main things: the people in the space and the building itself plus activities in the space.
Okay.
So RP is the rate needed per person. That covers stuff people generate, like body odors, bioeffluents. CO2 is often used as a stand-in measure for those. P is just the number of people in the zone. You can use default numbers from Table 6.1 if you don't know the exact occupancy.
Got it. People part.
Then RAC is the rate needed per unit area per square foot or square meter. That handles contaminants coming in from the building materials, furniture, cleaning products, things like that, as is just the floor area of the zone.
Okay, so you add the people air part and the building air part together, and that's your target for the breathing zone. Can you give an example from that table 6.1?
Sure. Let's take a standard office space. The table says you need 5 centimeter cubic feet per minute per person, plus 0.06 centimeter per square foot of floor area.
Okay. What about something else, like a classroom?
A classroom for older kids, say age 9 and up, that's higher per person, 10 centimeters per person, plus 0.12 centimeters per square foot. A restaurant dining area is 7.5 centimeters per person, plus 0.18 centimeters per foot. The table has dozens of space types listed.
So you literally just look up your space type, find the RP and RA values, estimate the people, measure the area, and do the math.
That's the core of it, yeah.
All right.
But wait, there's more.
Uh-oh.
Even the VRP has a couple more layers to make sure that calculated air actually gets delivered effectively. First, there's zone air distribution effectiveness, or ES, section 6.2.2.2.
What's that about?
It recognizes that how you supply the air into the room matters.
Yeah.
Are the vents in the ceiling and the floor? Is the supply air warmer or cooler than the room air? For example, if you supply cool air from the ceiling and have the return vent down low, the air mixes pretty well, so your ES might be 1.0, meaning it's fully effective.
Right.
But if you supply warm air from the ceiling and also return it near the ceiling, that warm air might just pool up high and not mix down well. In that case, your ES might be lower, maybe 0.8.
And if ES is lower?
It means you actually need to supply more total outdoor air into the zone, vols equals the VBZ ES, to make sure the breathing zone still gets the target amount, VBZ. You have to compensate for the less effective delivery.
Okay, so ES is about getting the air to the people within the room. What if you have one big air handler serving multiple rooms and it recirculates some air?
Now you're getting into system ventilation efficiency, F, section 6.2.5.2. This one gets pretty complicated, especially with variable air volume systems and recirculation.
Keep it simple. What's the core idea?
The core idea is that when you have a central system mixing outdoor air with return air and sending it to multiple zones, not all the outdoor air you bring into the main air handler necessarily makes it as fresh air to the worst-case zone at any given time. EV accounts for this whole system. In fact, how efficiently the outdoor air gets distributed to the zone that needs it most. It tells you how much total outdoor air you need at the main intake, to satisfy the requirements of all the zones. Appendix A has the detailed calculations.
Okay, so even the recipe book VRP involves checking how air moves in the room and how it moves through the whole system to make sure people actually get the fresh air calculated from RP and raw.
Exactly. It's prescriptive, but not that simple. And the VRP section also covers exhaust ventilation requirements, section 6.2.8. Certain spaces, like restrooms, kitchens, labs, need dedicated exhaust fans pulling air out at specific rates, listed in Table 6-4.
Got it. Okay, that's the VRP. What about the other one, the IAQ procedure?
Right, the IAQ procedure, section 6.3. This is the performance-based method. The insight here is flexibility, but it demands a lot more upfront work and expertise.
Performance-based, meaning you don't use the tables.
Correct. Instead of using the standard RP and raw values, you do a detailed engineering analysis focused on the specific contaminants you expect in your particular building or space.
So you figure out exactly what pollutants are likely to be there and design to control those specific things.
Pretty much. You identify the contaminants, figure out where they're coming from, sources, estimate how much is being generated, emission rates. Then you set specific target concentration limits for those contaminants.
Where do you get those limits?
You look at guidance from cognizant authorities like EPA, maybe OSHA, World Health Organization. Appendix B lists a bunch of sources, but also cautions that you shouldn't just blindly apply industrial workplace limits to a general office population, for example.
Okay. And you still need that 80% satisfaction goal, too.
Yes. The perceived air quality goal, assessed by occupants, usually relating to odor and irritation, is still part of it. Then you use engineering methods, often mass balance analysis. Basically tracking the pollutant, how much comes in, how much goes out, how much is generated inside, how much is removed by ventilation or air cleaning to figure out what ventilation rate or what other control measures you need to meet your target concentrations and acceptability goal. Appendix D gives some equations.
Wow, that sounds way more involved. What's the payoff? Why do it?
The big advantage is it allows you to potentially get credit for things other than just bringing in tons of outdoor air.
Like what?
Like using really good air cleaning technology, maybe filters much better than MRV6 or special gas phase filters to remove specific chemicals or odors. Or maybe you carefully select building materials and furnishings that have extremely low emissions.
Ah,
If you can prove through your analysis that these measures will achieve the target contaminant levels and perceived acceptability, you might be able to use less outdoor air than the VRP recipe would have required.
which could save energy, right? Heating and cooling all that outside air costs money.
Exactly. Energy savings is often a major driver for using the IAQ procedure, but it requires a lot more design effort, detailed knowledge of contaminants, and often ongoing monitoring and validation to prove it's actually working as designed.
And you mentioned subjective testing, people sniffing the air.
Yeah. Appendix B mentions that perceived acceptability can sometimes be evaluated using panels of people. But it stresses, and this is important, those subjective tests only capture things like odor or sensory irritation. They won't tell you if there's odorless carbon monoxide or radon present. You still need objective measurements for health hazards.
Okay, so summing up the two approaches. VRP is the standard recipe, prescriptive, generally easier to apply based on typical assumptions. IAQ procedure is the custom science experiment, more flexible, performance-based, can account for air cleaning and low-emitting materials, but way more complex to design and verify.
That's a really good summary.
All right, we've got the system designed using one of these procedures. Now we actually build it and run it. Section 7 covers the construction and startup phase.
Yeah, and the insight here is pretty simple. Don't mess up a good design during construction.
Right.
Little things matter, like don't run the ventilation systems without filters installed during construction.
Why not?
Because you'll just suck all that construction dust and debris deep into the ductwork and coils, and it's really hard to clean out later. It can become a source of problems down the road.
Makes sense.
Also, protect building materials, especially porous ones like drywall or insulation, from getting wet. Don't install anything that has visible mold on it. If non-porous stuff like metal gets moldy, it needs to be cleaned properly before installation.
So basically, keep the site, and especially the HVAC components, clean and dry throughout construction.
Exactly. Then comes system startup. Before you hand the building over, you have to test and commission this system.
What does that involve?
Critically, testing and balancing. An independent agency usually comes in to measure the actual airflow at diffusers and intakes to verify it matches the design rates, making sure febays, VAs, VOD are all being delivered as planned. You also have to test drain pans under cooling coils to make sure they actually drain properly. Standing water is a big no-no for mold. The system needs to be clean inside before it's officially started, and you test the outdoor air dampers to make sure they open and close correctly, controlling how much fresh air comes in.
Seems like a lot of checks, but essential to know it works right from day one. And all this needs to be written down, right? Documentation.
Oh, absolutely crucial. Section 7.2.6 and Section 8.2 hammer this home. Detailed documentation must be provided to the building owner or operator.
What kind of docs?
Things like the operating and maintenance O&M manual, info on the HVAC control sequence, the final air balance report showing the measured flows, the design drawings, and importantly, a summary of the design criteria and assumptions like what occupancy levels and space types were used for the VRP calculations or the targets and analysis for the IAQ procedure.
Wow.
And that O&M manual isn't just something to file away. It needs to be kept and actually used for the entire life of the system.
Which highlights a massive point, doesn't it? Building the system right is only like half the job.
Maybe less than half. Operating and maintaining it correctly over the years is just as vital, if not more so, for actually maintaining that acceptable indoor air quality.
And that's Section 8, Operations and Maintenance.
That's the whole focus. The standard requires the system to be operated and maintained according to both the standard itself and that specific O&M manual provided at startup.
What are some key maintenance tasks listed?
Table 8.1 gives a good list with suggested frequencies. Obvious things like checking and changing filters regularly. inspecting cooling coils and cleaning them if needed, checking drain pans to make sure they're clear and draining, checking fan operation, humidifiers if you have them.
What about the outside parts?
Yeah, inspecting the outdoor air intake louvers and screens at least every 6 months, looking for blockage from leaves or debris, making sure the bird screen is intact. Also, checking sensors used for control systems, do they need recalibration?
Seems thorough. What happens if during maintenance you actually find mold or standing water?
Sections 8.4.2 and 8.4.3 are very direct. Visible microbial growth or significant water accumulation found anywhere in the system must be investigated and remediated promptly. You can't just ignore it. It ties right back to those material requirements and drain pan tests. Find it, fix it.
Okay. What if the way the building is used changes over time? Like an office floor gets converted into a high-density call center.
Good question. Section 8.1.3 covers that. If the building use changes, or the occupancy density goes way up or down, or there are major renovations, anything that makes the original design assumptions invalid, then the ventilation system's design, operation, and maintenance plan should be reevaluated by someone qualified.
Because the original design might not be enough anymore.
Exactly. What worked for a standard office might not work for a crowded call center or a different type of activity.
One last thing. Existing buildings. It sounds like this standard is mostly written for new construction or major renos. What about older buildings?
Appendix G gives some guidance there. The main insight is that applying the entire standard retroactively to an old building might just not be practical or feasible.
Okay.
But the principles of the standard checking outdoor air, proper filtration, controlling sources, maintenance, those absolutely can and should be used to guide improvements in existing buildings.
So you don't have to rip everything out.
Generally not for simple repairs.
Mm.
If you replace a major component, like an air handler, ideally the new component should meet the current standards requirements from Section 5, though there might be exceptions for just replacing like for like if the old one met code back when it was installed. But if you do a substantial alteration, that's more likely to trigger broader requirements to meet the current standard.
So even for older buildings, the standard provides a roadmap for making things better, even if you can't hit every single requirement immediately.
Precisely. It's a framework for assessment and targeted upgrades.
Wow. Okay, this has been a really, really deep dive into ASHRAE 62.1-2007. Let's try to recap the big takeaways, the key insights. Acceptable indoor air quality. It's this blend of objective health protection, no harmful contaminants, and subjective human comfort, keeping most people satisfied.
Right, and it all starts with looking at the air outside the building first and being careful about where you bring it in, avoiding those local pollution sources.
Then the system design itself is critical. The materials air touches shouldn't grow mold or fall apart. You need filters, you need humidity control in some cases, and crucially, you need access to maintain everything.
Don't forget classifying the air inside class 1, 2, 3, and making sure you don't recirculate dirtier air into cleaner spaces. That separation is key.
And calculating how much air. Two main paths. The prescriptive VRP, that recipe book using rates per person and per area, but with those important tweaks for air distribution and system efficiency, Eve.
Or the performance-based IAQ procedure, the science experiment approach analyzing specific contaminants and potentially using air cleaning or better materials to meet targets, possibly with less outdoor air, but much more complex.
And finally, none of it matters if it's not built right. Started up correctly with testing and balancing, and then operated and maintained diligently over the long haul, following that O&M manual. Documentation ties it all together.
You got it. And understanding this standard, even at this level, hopefully gives you, the listener, a real appreciation for the kind of hidden infrastructure that's working, or maybe should be working, to protect your health and comfort in those buildings you use every day.
Yeah, the office, the stores, schools. It directly impacts the air quality you experience there.
Exactly.
And maybe one final thought to leave people with, drawing from that Appendix B discussion. Even with all these incredibly detailed tables, formulas, tests, specific rules, achieving what feels like acceptable indoor air quality still bumps up against that tricky, subjective human element, right?
Yeah. People's perception of smell, irritation, stuffiness, not always easy to measure.
Yeah.
And then you have the sheer complexity of the indoor environment. Thousands of different chemicals potentially interacting in ways we're still figuring out.
So the provocative question for you, the listener, might be, how do we best balance all this? The hard science, the engineering calculations, the regulations, with that very real but sometimes fuzzy human experience of whether the air feels good or not.
And how does our constantly evolving understanding of indoor pollution continue to push and reshape these standards for the future? It's an ongoing process.
Definitely something to think about next time you walk into a building and just take a breath. Maybe you'll notice where the vents are or wonder when the filters were last changed.
We hope this deep dive has given you a fresh perspective on the air all around you.